This is Fan of Astronomy, Episode 2.
10, 9, ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
Welcome back to another episode of Fan of Astronomy. This will be our second one. I am your host, Angelo. I'm here to bring the fart jokes. And I brought with me Dan again.
Hi, Angelo.
He's here to bring knowledge.
Okay.
Well, it sounds better because of your accent.
Oh.
People just naturally think, oh, he has an accent. That means he's more intelligent. So.
Good for me.
Yeah, I'll bring the fart jokes. You bring the intelligence. It works. So Dan is the Swedish superstar? Yeah, that's what I called him last week.
Yeah, you did. And I was like, okay, sure. But you have been podcasting longer than I have. Your old podcast was bigger than my podcasts. And I was like, oh, no, sure, I'm a superstar. But you know what?
Turns out I was right. I'm prophetic.
Yeah,
right?
you were right.
So what happened?
On Friday, the 18th of November, sorry. This week has been hectic. I noticed that my serial killer podcast in Swedish was getting enormous numbers on the server. And I was like, oh, something is wrong with the server. But no other podcast was moving. So I was like, what's going on? And then people started sending me congratulation messages. And, what? It's not my birthday. And then I was number 1 on Swedish iTunes.
Wow.
A couple of days later, I was number 1 and number 16 on Swedish iTunes with my Murder of the Swedish Prime Minister podcast.
So people like to listen to people getting killed is what you're saying?
Yes. Swedish people like murder, apparently. So, and then the server broke and Fan of Astronomy went down with it.
Which is a shame in a way because we went through all that work to get iTunes approved right away and posted on all these different places, and then it disappeared right away.
So I have been running all my podcasts from a server that my YouTube partner with the YouTube channel Magic Gathering Strat, he is administering the server. And it's been working great since early 2013. And now it broke under the pressure of 100,000 subscribers to this serial killer podcast. So I fell down to number 17 on iTunes because you couldn't get the podcast. So I put it up everywhere on the web I could. That wasn't iTunes. Then the server came back up, and now I'm back at number 2.
That's cool. I mean, it's a good problem to have in its own way. It stinks to drop all the way to 17, but at the same time, the fact that you had so many listeners that it crashed your server, like, that's a good problem. As long as you get it back up quick enough that those people don't disappear forever. Yeah,
and of course there's a huge delay with iTunes because most people had just downloaded it and not listened to it yet. So they were fine because they already had the file. But I'm of course working on a more long-term solution. So this week I'm talking to a couple of companies like podcast networks that will take over everything that's boring with my podcasts and give me some studio access. I will even try to make them build me a home studio like yours because I'm so envious of your studio.
It's not that special, man.
It's special compared to where I'm sitting right now.
Probably true, but I mean, it was only a few $1,000s to build this.
So for the time being, my English podcasts will stay on this server where they are, and I will remove the Swedish sinners from it. So we should be fine now for our future episodes.
Just like a Swede, you're staying so neutral. You're like, I'm going to take the Swedish ones and I'm going to put them over there, and the American ones will be over here, and everything will be good.
Yes, that's the plan.
That's so Swedish of you.
Yeah, that's the socialist plan.
Well, this is the way we get paid for our show, and that's through patreon.com/astronomy. It's a small cost for large content, plain and simple. Basically, we're asking for at least $2 per episode if you can afford it, which is only $4 a month. This is less than buying either one of us lunch. We're not even trying to eat off of you. But if we get enough people, we can buy a good lunch, right?
But please don't buy me $4 lunch. That sounds horrible.
Yeah, that actually does sound pretty bad. That sounds like gas station food.
Yes. Like old sausages at the gas station, like hot dogs from last year.
But Dan, we do have some special incentives for our Patreon listeners if we hit certain marks. You want to tell them about that?
Oh yes, we have bonus episodes, and the first one is at the $100 mark. And if we hit that together, we'll do an episode about how the universe wants to kill us.
Yep. Everything in the universe is acting against life.
Yes. We also have individual rewards. You will get an official thank you in the podcast if you sponsor us with $2 an episode. If you sponsor us with $5 an episode, you get to ask questions in the podcast. And there might even be more rewards. So check them out at patreon.com/astronomy.
Yes. So today we have a massive topic.
It's huge.
I mean, absolutely the biggest thing in our solar system, and without it, we could not exist. And of course, I'm talking about the sun.
I was walking today, and I was like, you learn very early not to stare at the sun. But I was thinking about this episode, and I was like, I'm gonna try to get a peek of it. And it's like so weird, this giant fireball in the sky.
Uh-huh. That's
it's
exactly.
Close. 150 million kilometers. It's not that far away.
It is not. One of the things that we need to go over, though, is first thing, our sun is actually a star.
Oh, yes.
So we need to talk about what stars are, just because without having that base of knowledge, well, I guess you could get away with it without having that base of knowledge, but nonetheless, it's good to have that base of knowledge of what a star exactly is. And what it exactly is a luminous plasma sphere that's held together by its own gravity. And it relies on thermonuclear fusion of hydrogen into helium. And that's where we get its shine. And all stars, all of them, are born and they die. Just like everything else in the universe, stars die. The birth of a star is typically the start of all solar systems, as planets are usually just the leftovers that the star doesn't use, which is pretty interesting.
That's pretty interesting. Jupiter, quite a large leftover.
Yeah, to think all of that got pushed out there. I mean, when you think about it, it's not just Jupiter. It's all those gas giants out there that it just said, yeah, we don't need that. And if it took it, we might have a larger size sun.
Yeah, but it would make very little difference because the sun is still 99.86% of the mass in the solar system.
That's a scary thought.
Yeah, so everything else is just gravy on top of the sun.
Yes, yes. So we have different types of stars. Dan, do you know all the types of stars?
I do have a list in front of me. So
that helps.
Yeah.
Cheater.
Yeah. You wrote the list.
I did.
Well, the most common type of star is the M-class star. And the sun is a G2V star, making it kind of rare, actually. The M-class stars are the red dwarfs. Proxima Centauri is a great example of it. We talked about it last time.
Mm-hmm.
They're small for stars, and they're not very hot on the surface. We're talking about 3,000 to 4,000 kelvins, or Celsius. There's pretty much no big difference when you talk about Kelvin and Celsius on such hot things.
Okay, but this is an English-speaking podcast, so I'm hoping that a lot of Americans are listening. So I'm thinking Fahrenheit to Kelvin is a huge difference.
Okay, what's the Fahrenheit of a red dwarf?
I honestly have no clue.
Okay,
I wish I
somebody
could tell
answer
you
us
I
in the comments.
did, but I got all of my temperatures in Kelvin, and when you're dealing with temperatures at this range, Kelvin's a better way of going.
Yeah, definitely. Kelvin, it's the same difference between degrees as the Celsius scale, but we start at absolute zero at minus 273.15 degrees Celsius. So there are no negative Kelvin degrees because at 0 Kelvin there is no heat at all, no motion among particles
Yeah,
or
that is
atoms.
absolute zero.
It's cold.
Yes. And what color are these stars?
The M-class stars are red, and by far the most common types. Then if you go a little bigger, you get to the K-class stars. They are about 1,000 degrees hotter. Epsilon Indi is a great example of a K-class star, and they are usually called orange stars. And they are much more similar to the sun than the red dwarfs.
Mm-hmm.
And then you get to the G-class, the yellow dwarfs, also called yellow stars. And then we're talking about the sun. And the sun has a surface temperature of around 5,500 kelvins. The sun is a G2V, meaning that it's not the smallest of, or not the coolest of yellow dwarf stars.
No, it's actually right in the middle of it.
Yeah.
Which is pretty good.
Yeah, and about 85% of the stars in the Milky Way are smaller than the sun. So the sun is a pretty big star, but there are stars that are enormous compared to the sun. But still, it's not like the most common star at all.
Nope.
Also, being alone like the sun is, not having a partner in life, is quite rare as well.
Oh, it's so single. It needs to get Tinder.
I don't think we would appreciate another star hooking up with the sun at this point.
But the sun might like it. Ever think of its feelings?
Yeah, like if Sirius showed up and courted the sun, bringing its white dwarf, that would suck.
Yeah, probably. For us.
Want to proceed with the star classes?
Sure, I can do that. After that, we get to the F class, which is about 6,000 degrees to 7,200 degrees Kelvin. Procyon A is a good example of that, and these tend to have a color of yellow to white. They kind of flare into those colors. And you'll notice when I go over these temperatures and when Dan does, there's usually a gap. And that is because sometimes these stars flare up and they get a little hotter than, like Epsilon Indi, it says it can get to 5,250 Kelvin, but G class doesn't start till 5,500. Well, what happens at that 250 degrees? They can flare up and get angry from time to time, so they give it a little bit of room there. Our next class is our A-class stars, and this is 7,500 to 10,000 Kelvin. These are hot stars. Altair is probably the best example I could come up with, and that is a white star. These things are enormous.
They are huge.
But they're not the biggest.
No, not at all.
We have B-class stars on top of that. Rigel is one of those. 10,500 degrees to 30,000 degrees Kelvin. These things shine a blue-white hue. And
That's
then,
a bad sign.
Yes, and then we have O-class. Zeta Ophiuchi. I probably mispronounced that, but we're going to go with that. This is a blue star, and a blue star is basically any star that gets to 33,000 degrees Kelvin or more. So we have other types of stars, things that we call stars that aren't necessarily stars. And I'm going to go over the real quick list of normal names that you're going to hear us say. Brown dwarfs, white dwarfs, red dwarfs, subdwarfs, dwarfs, subgiants, giants, bright giants, supergiants, hypergiants. Now those all fit in those classes. Even though like a brown dwarf isn't red, it still fits in that class. And we have
We'll probably do an episode on each type of these because they are super interesting.
Absolutely.
There's also the mythological black dwarfs that do not exist yet in the universe.
Yeah, I looked at them and thought about putting them on there, but since there's no proof of them,
yeah, they will be there. It will just take a couple of trillion years.
Yeah, I mean, it's going to take time, but they don't exist now, so I felt like it probably shouldn't be talked about yet, because it's more a long-term theoretical thing.
Let's talk about it in a couple of trillion years then.
Yeah, well, look, real quickly, it's when a sun completely dies, because the suns die, and then it takes a while for them to decay, and after it's decayed, then you get a black star. Got it? Okay, then we have these very special types of stars. I'll go over some of these, and then I'll let Dan take the rest of them. We start with methane dwarfs. These are things like Jupiter, but much bigger, but not quite stars. Okay? Then we have Wolf-Rayet stars, which is its own type of star. We're going to have a whole episode on these crazy ones. Then we have slash stars. Yes, I said slash stars. No explanation behind it, because you don't need it. Then we have class L dwarfs. Then we have substellar objects. And Dan, I'm going to give you these last five, which are probably the most interesting of the five.
Yes, they are super interesting. There are carbon stars, which I'm not sure what it is. Is that white dwarfs? White dwarfs are pretty much carbon stars.
Fairly, yeah.
Neutron stars then, which happen, neutron stars and black holes. I'm going to talk so much about them, so let's just skip them here. We've got exotic stars, which are very interesting. But I like to talk about the difference between Jupiter and the smallest of the red dwarfs, the smallest of the M-class stars. To be a proper star on the main sequence. The main sequence is like the normal lifespan, the sort of adult life of a star. And the red dwarfs are the smallest stars on the main sequence. And a typical small red dwarf is about 100 the mass of Jupiter. So Jupiter is sometimes described as a failed star, but Jupiter is way too small. It's made up of the stuff that stars are made up of, but it's so small that it will never ignite hydrogen and make it into helium, which is like the thing that stars does. But if you go up a bit, if you get to 10, 15 Jupiter masses, we are getting the brown dwarfs. These are objects that are too big to be planets and too small to be stars. So they will sometimes ignite hydrogen. So they can have like star-like periods, and then they go back to being planet-like. And they are a very different animal in this classification object. So the difference between a planet and a star is kind of fluid when you get to 10 to 15 Jupiter masses. And a strange effect is that as the size, if you look at it, a 15 Jupiter mass planet will have about the same size as Jupiter, because there's a physical function that limits the size of substar objects. So it will be much denser, but it will still look to be the same size as Jupiter. Yeah, that was my brown dwarf spell. So
Okay.
We'll talk more about brown. There are plenty of brown dwarfs in our vicinity, and we just recently found them.
Yep. I do have a little bit on the exotic stars that I did want to bring up. We have many different types of exotic stars, okay? And these things are interesting because they're all compact stars. So they expect these things to be small, but at the same time, extremely hot. And if not extremely hot, we're talking extremely hot in the form of gravitational fields or radiation. They might not be heat as we know it, but these things are there. Like one would be called like a quark star. And this happens in the decomposition of neutrons. And
Have we found any quark stars yet?
no, these are all hypotheticals.
Okay.
This should be said. These are all hypotheticals, but the science does back them up. We have electroweak stars, which is just radiation pressure from a single object. Again, very, very small. But the process basically says that this star is about the size of an apple, but it contains 2 Earth masses. Think about that.
Yeah.
You take 2 Earths, shove them together until they're the size of a frickin' apple. That's a lot of pressure. We have preon stars, and this is another subatomic particle that very theoretical, and it has a density exceeding 10 to the 23rd kilograms Earth mass to the third.
Yep. Nice.
So big, okay? I mean, very small, but very big at the same time. Very strange. Then we have bosons.
These are all corpses of stars, right? Just like white dwarfs, neutron stars, and black holes.
That's the thought.
Yeah.
Since they're all theoretical, we have a hard time really saying exactly how these are going to create.
Because when a star dies, when it leaves the main sequence, bad stuff happens.
Usually.
I'm going to talk in detail about what's going to happen to the sun.
Yes.
But what's left depends on the mass of the star, and sort of the ultimate product of the ending of a main sequence is a black hole for a large star.
Right. So then we have boson stars. Okay.
Oh, no.
And these things, basically, the way we believe they're going to happen, when it's all said and done, they're going to have halos of dark matter around them. Okay. Kind of crazy there to think about that. Everyone should know what a boson is. The famous Higgs boson has just, a few years ago has been discovered. It is a very subatomic particle. Okay.
Yeah, future episode for sure.
Then we have the Planck star, or the Planck star. This is a theoretical star that they believe is in the middle of a black hole.
Oh, okay.
The idea is based completely on loop quantum gravity. I shouldn't have to get much further into what loop quantum gravity is. Just know that it sounds impressive.
Yeah, please don't go further.
So this is something that it's like, whoa, wait, what? Yeah, they believe that there's stars inside of black holes, because a black hole, like Dan said, is the death of a star. But sometimes when stars die, they leave stuff behind, and this thing might be in the middle of it, just burning away, but the black hole is sucking up light that we can't see them.
Wow.
Yeah, so this thing would be extremely dense. Stupidly dense. So I think those are all interesting types of stars, and that's why I wanted to bring them up. Glue balls is another type, and Q stars.
I know all about blue balls.
Yes, glue balls, not blue balls.
Oh, sorry.
That's his accent. Deal with it.
Of course, yeah, let's blame the accent.
Blue balls is something completely different.
And when we talk about the main sequence stars,
yes,
the M class to the O class, there is a pattern there. So the hotter it gets, the bigger they get usually.
Yep.
and the shorter the lifespan gets, because as I said in last episode, I think the red dwarfs, they will live for trillions of years, whereas our sun has a 10 billion year expiration date.
Yeah, it's kind of like the saying that we have here in the States where I don't know if it's a worldwide saying, but I know we have it in the States, where the hotter you burn, the quicker you burn up.
Yeah, we do have that saying too.
Okay, so that's basically the stars, just go off of that saying. The hotter it burns, the quicker it's going to burn away. So, which
is why the bigger the star, the poorer candidate it is for harboring life. Of course, you don't want to live around Zeta Ophiuchi. That's a bad place to be, because that place is going to blow up.
And when that does, because it's such a big star, it's going to leave something. It's going to leave either a neutron star or a black hole behind.
Yeah, Zeta Ophiuchi is a clear black hole remnant.
Could possibly leave a neutron.
Could it? I think it's way too big, isn't it?
I don't think so. Is it?
I think the difference is 5 solar masses.
Okay.
For a star, to become a black hole. But we'll talk more about the stellar remnants in a later episode.
Fair. So continue talking about our star, sir.
Yeah, the sun. One interesting thing about the sun is that it is actually white, which you can see very clearly from any picture taken from space. Of course, it only turns yellow because of the atmosphere. And if you look at the sun in weird angles from the Earth, it can also be red or orange.
Uh-huh.
And that's just our atmosphere. It's totally white. It's really, really white. Except when it has sunspots. And the sun has a huge magnetic field. Because different parts of the sun are moving at different speeds, and there are metals in the sun. So, and the sunspots they occur when the magnetic field crosses the sun's surface. And they do work on a kind of 11-year schedule, or 11-year cycle, but there are other cycles in the sun. So, the life of sunspots is an interesting subject in itself. But what you should know is that when you see a sunspot, it's the magnetic field lines crossing the surface of the sun. Should we talk about the interior makeout, how the sun is, what it consists of?
Sure. Go for it.
The nuclear explosion itself, the sort of thing that makes a star, it's happening in the core of the sun. So we don't see any of that. And we only see like the smoke from it, which is the surface. And the photons of the sun are created in the core, and there is this balance between the explosion itself and the enormous gravity of the sun, which puts the sun in this 10 billion year long equilibrium. It changes a bit, but sort of it makes the sun have this really long, stable life. So if you're a photon created in the middle of the sun, it's extremely hard to get out of the sun. You will just bounce around, be absorbed, and then bounce again. So you'll be spending millions of years jumping around inside the core of the sun before you find your way out. And once you do, it only takes 8 minutes and 19 seconds to get to Earth.
Yes, which is very neat. We call that an astronomical unit. But think of it this way. If you do something stupid like stare at the sun like Dan did earlier today, you're actually looking 8 minutes into the past. That's not where the sun is located.
That's so hard to think about, especially when you look at stars other than the sun.
Yeah, I mean, and every star we get at further on, almost every object we see in the night sky, short of like the moon, it's legitimately in the past. I mean, the moon is too, but it's so short that it's not even worth bringing up. But the sun is 8 minutes. So for every astronomical unit, that's 8 minutes, 19 seconds into the past you're staring. So when we look off at these far galaxies, hundreds of thousands of light years away, we're talking hundreds of thousands of years into the past we're seeing.
They might not actually be there anymore.
Yeah, they could be gone.
Yeah.
That's one of the neat things about when you really think about this is you're used to you turning on your light in your house and the light comes right on. Well, there is a very, very, very slight, unrecognizable to human eyes or any animal's eyes, slight delay. And the further you get out, that delay becomes longer and longer, and it takes that long for that light to reach us. And you're actually looking into the past. Crazy.
Yeah, and if you look far away, far enough away, you can see the beginning of the universe. That's hard to think about.
Very.
In the core of the sun, we have a 15.7 million Kelvin temperature, so it's much hotter than the surface.
Yeah, the surface is only 570 5,772 degrees Kelvin on average.
Yeah, the surface is called the photosphere. There are 3 layers of the sun between the photosphere and the core, and I'm not going to get into them. But outside, in the chromosphere and in the corona of the sun, when you get a bit, this is so counterintuitive, and people are still debating why this is, as far as I understand. Because if you get to the corona of the sun, you experience an enormous temperature increase. So we're talking 2 million kelvins outside of the sun. But the density of particles in the corona is so small that if you would travel through this place quickly enough, you would not experience this temperature, but you would still be, of course, way too close to the photosphere to be comfortable. But if you stay in the corona, then the small amount of particles there will eventually heat you up to 2 million degrees Kelvin, and that would, of course, be unpleasant.
You'd be charcoal, man.
The last thing, if we look at the sun as a onion of layers, the last thing we should talk about is the heliosphere. That's sort of the area in space that the sun affects with its, where the sun is more powerful than the rest of the galaxy. And this extends far beyond the Kuiper belt, along, and let's see if I get, it's more than 50 AUs out. So it's beyond the planets, beyond the dwarf planets, most of them at all. And in December 2004, Voyager 1, the good old spacecraft, actually left the heliosphere. And when you leave the heliosphere, when you're finally outside the influence of the solar wind, then you are truly in outer space. So you left your backyard of the solar system, and you are free from the sun.
See, I still question that, and maybe it's because I'm just dumb, but we still have the Oort cloud out there, which it hasn't quite gotten through the Oort cloud. And the Oort cloud is obviously being held gravitationally by the sun.
Yeah, forget the 50 AU, that might be wrong.
Yeah, it should be
much longer out.
It's way beyond the Kuiper belt, but
the Oort cloud can go as long as the Oort cloud is still something that needs to be explored further, but it could go as far as 1 light year.
Yeah, we haven't figured out the edge of that, but this is basically something that it's way at the very end of our solar system, and it is being gravitationally held together, we believe, by our star. We could also share parts of our Oort cloud with another star.
Yes.
So we're not really 100% sure on where this thing ends, but it does have some influence from our sun.
We'll go, the place where the heliosphere ends is called the heliopause. And when we do this walkthrough of the solar system that we have started now, we'll go through everything. We'll end with the Oort cloud and the heliopause.
That'll be a quick episode because we don't know a lot about it.
Yeah, we'll still talk about it. We can make up stuff like Hobbit ninjas.
Hobbit ninjas, yes.
If there are Hobbit ninjas, they are not in the Oort cloud.
That we know of.
Yeah, they will be cold Hobbit ninjas.
So they would be... Okay. All I can think of is that bad Christmas special with Friesmeister.
Something like that.
Yeah.
Yeah, we mentioned last time that we are 27,200 light years from the center of the galaxy, and it's more interesting for the Earth, I think, than it is for the Sun.
I suppose, but if it's more interesting for the Earth, but it's also very interesting for the Sun because, again, we said this before, if the Sun wasn't exactly where it is at, bad things could happen.
I guess you can think of it like here in the suburbs, the Sun is king of its area. It's like the biggest thing around, and it has some peers living nearby, like the Alpha Centauri A and B, and it's happy. But if the Sun was in the center of the galaxy, it would be in danger.
If it was in the center of the galaxy, it'd be gone.
Yeah,
just saying.
In the supermassive black hole, it would be gone.
Just saying, it would be gone. The Sun is made mostly of 73% hydrogen and 24% helium. The rest is trace elements.
And we should be happy that there are 73% hydrogen left because it's burning hydrogen. And when it runs out of hydrogen, it is going to die.
It will. It will. But we should talk about some interesting facts about the Sun before we talk about how it's just going to go away.
Yes.
First off, the Sun is Sunday is named after the sun, obviously, and it's named after the Roman sun god from a cult who called their god Sol Invictus, meaning the unconquered sun. Sol is kind of another name that people do use for the sun. And
yes, it's actually the name we use in Sweden. We call it Solen.
Okay, so that makes sense. And Emperor Aurelian actually made it an official cult, and it became the patron of soldiers during the Roman Empire.
We both love history, but you are on a dangerous path now. We are starting to talk about Roman emperors. Because if we are talking about Sol Invictus and Roman emperors, you have to mention the guy named after the sun, the Roman emperor Elagabalus or Heliogabalus, who was the Roman emperor from 218 to 222. He was assassinated at 18 years of age. Because he was unbearable. You just had to kill him.
Yeah,
this is one of
hot.
the worst Roman emperors ever.
Just one of the worst. That's the bad thing to say. It was one of the worst.
Yeah, he has some competition, but I have to tell you about this guy.
Okay, that's fine.
Because he had been put away in Syria because he wasn't a direct heir. And he was like, this guy could be dangerous. Let's make him high priest of this weird sun cult in Syria. So there he was, thinking that he would spend his life as the high priest, and he got into it a lot. But at 14, politics happened, and he became the emperor. And he came to Rome, and he was different. Another name for him is Emperor No Pants, because he liked to dress up as a girl. He liked to dance naked through the streets of Rome. And he very much liked to have rough sex with his German bodyguards. And he liked to do that in public.
Well, who doesn't?
So the Senate was kind of, we miss the days of Augustus. And he could keep this up for 4 years until he was assassinated, and they put his cousin, who was only 13, on the throne, heavily monitored by his mother, so that he wouldn't do the same thing.
Ooh, I love history. So that guy was named after the sun. Aurelian, like I said, he made it an official cult.
Yeah, and Aurelian was like 50 years later. I think the sun cult took a hit because of Elagabalus.
A little bit, but but the sun became the patron of all soldiers because, no one can beat the sun. They knew that then, that if you got too close to the sun, you'd just burn up and you'd be done. No one can beat the sun. So that's what the soldiers went into fighting, is just, we got the sun at our back. We're fine. Plus, at that time, you didn't fight wars at night. That's how you lost. So the sun was very important to soldiers. Which makes perfectly good sense as to why they made him the patron of the soldiers. Now we're going to get into the fun stuff, and I'm going to talk about 7 billion years from now.
All right.
Okay.
7 billion.
Billion years. We have a couple years. Calm down, folks. Sun's going to expand.
Yep.
It's going to shed off its outer layers and just shoot that into the solar system. That part will probably kill us. Probably.
Yep.
If it doesn't, the sun will then continue to get bigger as the inner layers begin to swell as well. So what happens from there, Dan?
Well, I want to do this in detail because the sun is so very interesting and huge and important to us, and its death is often simplified to this. It becomes a red giant and then we die. So first we have the sun, due to the fact that the helium layer in the sun is getting bigger and bigger. The sun is getting hotter because the helium atoms in the core they don't occupy as much space as the hydrogen atoms. So the core is getting more and more compressed, more nuclear reactions, hotter sun, and this will actually affect us much earlier than the death itself of the sun. So I've heard very different numbers for this, but at some point the sun will become so hot that it will affect the oceans on Earth and create a runaway greenhouse effect using the most dangerous of greenhouse gases, water, to destroy life on the Earth. And I hear like from 50 million to 4 billion years for this to become a real danger to life on Earth. So we are at the end life on the Earth. This life on the Earth has been going on for a long time, and we're definitely way past the halfway point. But the Earth itself will be fine until then we run out of hydrogen. And when hydrogen ends...
Here's my thing, Dan. You say the runaway greenhouse effect.
Yes.
I have faith that humans are going to do that long before the sun does.
Actually, we can't, because the carbon on Earth, there is not enough carbon to create a runaway greenhouse effect like on Venus. So we can make it pretty bad.
We can make it unlivable.
We can't sort of steam away the oceans by ourselves.
No, but we can make it unlivable to where it no longer matters to us.
Yeah, we probably can, but I don't think we can make ourselves extinct just through greenhouse effect.
Oh, I'm sure we can. I'm quite certain we can.
We should probably look at that in more detail in a later episode as well.
Oh, no, we can do this right now because, one, we can melt the polar ice caps, which is going to basically jam people into very small portions of the planet.
Yes, where it will be hot.
Yes, it'll be very hot, and then once you get a bunch of people in, and this is all going to happen because of climate change, and for, those who don't believe it, get over it.
Yeah, climate change is real.
Yes, so those people are going to be stuck in very small portions. We've seen what happens historically when you get a bunch of people in very small, compact areas. That's when you get massive disease, massive plagues. And I mean, don't get me wrong, there's a lot of people living in London. There's a lot of people living in New York City. And under the current technology, we can kind of maintain the problem. But as it gets worse and people get jammed further in, it's only going to make things worse. So I think we can make ourselves extinct just through just sheer numbers of coming together, disease happening, and it's all a direct result of global warming or climate change.
Please care about the environment. That's a good idea.
Yes, go buy big cars.
The date for core hydrogen exhaustion is estimated as 5.4 billion years today. And at that point, the sun is double as luminous as today. So Earth will be receiving as much sunlight as Venus does right before the hydrogen runs out. And then the sun doesn't become a red giant because it will enter a subgiant phase.
Yes.
It will grow to twice its size. And this will take about 500 million years. But at the end of the subgiant phase, we get into another 500 million year long. This is how we reach the 7 billion year mark. Another 500 million phase where it grows into this enormous star, 200 times the size it is today. So it's pretty much like the size comparison between Earth and the sun today.
So
the sun will get that big again.
So let me get this straight. Right now, the general size, not density, of the sun is about 109 times the Earth.
No, that's the diameter of the sun. The sun is about 330,000 times.
Well, that's what I meant. I said not density. I meant just the diameter. If you were to take the Earth 109 times over itself, that's about the size of the sun. So it's going to do that again, you say?
Yeah, it's going to be 200 times bigger in diameter, and that's the red giant phase. So the red giant phase starts 6.4 billion years from now. But the sun still has about the same mass, so it's much less dense.
It's a big fluffy cloud.
Yes, and the red giant, it will swallow Mercury, it will swallow Venus, and there is a lot of debate whether it will swallow the Earth. But right now, most things I read says that the Earth is still there. The gravity from the sun is still the same. So the Earth is still in its orbit, but of course we have a red giant star really close. So it's bad to be on the Earth, but the Earth is still around at that point.
That's the thought.
Yeah.
There are some other thoughts that say that it will consume us. So either way, that's how close it's going to get. It's either going to be on our doorstep or it's going to be here.
And it's going to be a red giant for 1 billion years. And this is tough for the sun. So it will lose about 1/3 of its mass in this process, just dropping things because it's much less dense. And then the red giant branch ends. And the sun is still going to live for 120 million years because now it ignites its helium. And there's a helium flash. And this is a pretty traumatic event because 6% of the core will be converted carbon in a matter of minutes through something called the triple alpha process. And that's that's bad. That's really bad. And after the helium flash, the sun shrinks to about 10 times its current size. So it just leaves the sky and becomes something else. But it's super bright. it's 50 times brighter than today. And this is called the red clump. So this is really weird. And this is the point where some stars explode, but the sun is too small, so it can't do that. So it will hang around as a red clump for 100 million years, burning helium.
Yay. Oh, wait, we're dead.
No, the Earth is possibly still orbiting this thing.
Yeah, but we're dead.
As it still has roughly, as it loses mass, we go further out, which is good for the safety of the planet itself. But life will, of course, be long gone.
Yeah.
And then we enter sort of, helium becomes more and more rare. And we enter something called the early Asymptotic-giant-branch, where the sun becomes unstable. It's like, where is my last helium? Please, I need some more helium. And it will like be bigger, be smaller, be bigger, be smaller, be brighter. It will be crazy. And it will lose a lot of mass. It will send out dangerous pieces of the sun over like all the way onto the planets. And then we enter the post-asymptotic-giant-branch, which is where the sun just collapses and drops a lot of its mass, not all of it, not even a majority of it, but now it creates a new planetary nebula pretty much. It drops a lot of its stuff and shrinks to a white dwarf. And the white dwarf will be approximately the size of the moon, but it will still have 54% of the sun's mass. And the white dwarf will be about 100,000 kelvins hot, and it will take trillions of years for the sun to cool down. But in the phase where the sun was so unstable, the remnants of the Earth goes away. So the Earth will not be orbiting the white dwarf. So no memory of the Earth. We have to be gone by this time. And then trillions and trillions and trillions of years passes until the white dwarf finally fades into a hypothetical black dwarf. And that's the death of the sun.
So what happens to the Earth exactly when Dan says that it shoots us off? Well, if it doesn't get burnt up by the expansion, which, again, this is completely debatable still, no one's really 100% sure, the Earth may become a rogue planet.
That could happen.
Which is just a planet with no star that's just floating in the depths of space. And if that happens, and if for some reason there's still water here, I don't really see how that happens, but if for some reason it did, we would just become an icy ball in space, just floating forever until we either hit something else or get pulled into another star's gravitational pull.
And that's the absolute best case scenario for the Earth.
Yes, that is the absolute best.
The thing that in 2008 it was presented a theory that during the sun's sort of last spasms in the asymptotic-giant-branch phase, the tidal forces of the varying effects of the sun will slow Earth down, and it will fall into this dying star. That's one version.
Yeah, and that's, again, not one of the best.
That's the worst case. So rogue planet, good. Falling into dying star, bad.
I can get along with that. We can make that work. So
we probably have to leave within like 300 million years or so.
Now, theoretical ways to make the sun last longer. Here's a crazy one that has been proposed. You push Jupiter into it. Believe it or not, that would work. The only problem is getting Jupiter to the sun would probably throw every planet out of orbit. And it wouldn't give it all that much more time.
No.
But it would give it some more time. Probably, I've seen some scientists say almost 1 billion more years. But
okay, let's do that.
But, getting Jupiter past Mars, Earth, Mercury, Venus.
Yeah, I can see the problem, like, just coming through, ignore Jupiter, passing through.
Just stay where you're at. I'm coming through. Nothing's going to happen to any of you. Yeah.
No, Ganymede, you cannot crash into Mars.
Yeah, that's not going to happen well. And then I've seen people actually say that, you fire nukes into it because it's a big nuke itself. Yeah, that's not going to work.
There's not enough hydrogen in a nuke.
That's just not going to work. It's going to laugh at that. That's like when
in
you're
the
sitting...
end, humanity's only chance is to leave.
Yeah, that's like when you're sitting down really, really hungry, and they come out with this huge, huge platter in front of you, and they lift the top of it, and there's a single blade of grass. That's not going to fill you up. It's not going to fill the sun up. So get over that idea. That's not going to work. Have you heard of any other theoretical ways that we could prolong the sun besides what I've just spoke of?
Well, if you can bring Jupiter to the sun without killing us, perhaps you could just take a red dwarf and put it in the sun.
This is possible. We could throw a red dwarf into the sun. That would give us a ton of years.
Yeah, don't try that at home.
Yeah, that would be worse than throwing Jupiter into it. By a lot. You're not going to get past the Earth with a dwarf star. Just, no. Give up on that.
Another thing I thought about the sun. The sun is actually a pretty young star for the universe, and it seems to be made up of a lot of metal for a star. It's a pretty metal-rich star, and that's probably a requirement for life as well. So, and metals are created. Metals in star language is anything that's not hydrogen and helium.
Yeah.
And in order to become a metal-rich star, you have to be the result of a supernova. Something has to blow up because heavier elements are only created in supernova. We are all made of star stuff. And the sun had to be, I think it has to be a third generation star, that 2 supernovas have to go. The first stars, they're just pretty much just helium and hydrogen. And then that blows up, creates a heavier star, and then that blew up and created the stuff that we are made of.
Yeah. Yeah, I've heard that. So I can get along with that.
And it's probably this cloud of dust from that second generation star was probably disturbed by another supernova, which sort of made the sun come together. So we are this is a series of coincidences creating this perfect star for us. And it's not a common star. We should be grateful for the sun.
And very, very, very recently, they have discovered a rebirth of a star.
A rebirth?
A rebirth. This is very recent. So they're still trying to go through all the numbers to see if after this calculation in this, visual thing, what type of stars are going to do this. They haven't quite fully discovered that. So we don't know if our sun would be a rebirth, but more than likely, no.
So the star died and then found some new matter and recreated itself?
It basically pulled back in what it threw off.
Wow.
Yeah, very weird, very strange. It's been one of the clips on the Science Channel when they do the little news clips. We have a Science Channel in the U.S., and they've been talking about that for about the last week. So this is a very, very, very new discovery.
Oh, so it might end up in our news segments in a couple of months.
It very well could. But I thought that it was appropriate for this subject that, hey, now we know, stars can become reborn. And, who knows? Maybe our sun's one of those. Maybe it's not.
That's beautiful.
Yeah, it absolutely is. I'll have to shoot you a link to that at some point here, Dan.
Please do.
So what we're going to do is we're going to take a real quick break before we come back with our news, and I think we got something interesting in store for the news this week.
Sweet.
Hello. Are you enjoying the show so far? I hope you are. Well, if so, I encourage you all to pause the show. Don't worry, we'll wait. Go to facebook.com/fan of astronomy and hit that like button. You'll be one of the first people to know when a new episode comes out. Also, on that page, the guys post articles on the latest news in the astronomy field and outer space in general. You also get to interact with the hosts of our show, Dan and Angelo, there, so please hit that like button on Facebook. Thanks.
So now we got the news section, and this news is a very recent discovery. About the 14th of October, it was reported upon. And this comes from this is a gas giant, correct?
Yeah.
Okay, I had a brain fart for a second. I'm sorry. This comes from
or an ice giant, depending on how you label stuff.
Yeah, it could be an ice giant, I suppose, because it's so far out that it's cold. We'll get into that later. Anyway, Uranus.
Saturn.
Yeah, Uranus may have 2 moons that nobody's ever seen that we just discovered. And it's it's creating actually wavy patterns in the planet's rings. Yes, Uranus has rings. Neat. We just discovered them not too long ago. Yeah, well, I guess in a scale. We knew that
if you're a big planet, you have rings. That's at least in our solar system.
Yeah, that seems to be a pretty set rule. We knew of 27 moons, which is so much smaller than Jupiter, Saturn, with their 67 and 62 respectively. Yes, but now we found 2 completely black moons around Uranus.
Yeah.
So
They must be really small.
They are very small. One of them is about 4 kilometers, and the other one is about 14 kilometers. And they're extremely close to Uranus.
Yeah.
Which is pretty neat.
They're like shepherd moons of the rings.
Yes, I mean, we found out most of these moons from Voyager 2. It tripled the number that we knew during the 1986 flyby. But until we get something like Jupiter's Galileo or Saturn's Cassini, a satellite that is sent to specifically orbit this, there may be more moons for all we know. There may be less, and this may prove or disprove that these are actually moons. Because like we were talking last week with the Earth, there's a lot of things that for small periods of time we thought was moons, and then once we, put them through the computer calculations, we found out, oh crap, those aren't moons. So that's also a possibility.
Well, 4 kilometers, that's like Christmas size.
Yes, but Cruithne size next to the Earth is big. Cruithne size next to Uranus is tiny.
That's very tiny.
And so it's all relative, I suppose.
Yeah, when you think about the 4 big planets or the 5 big planets in our solar system, if you look at Jupiter and Saturn, they are quite close to Earth compared to planet 7 between Saturn and, which we're talking about now, between Saturn and Neptune. And Neptune is, of course, a long way away. So it's much easier for us to know stuff. We have explored Jupiter and Saturn a lot more than we have explored the outer 2 ice giants.
Okay, so this was discovered by the University of Idaho in Moscow. Have you ever heard of such a thing?
That's strange. So it's a part of their campus named Moscow?
No, it's in Moscow.
What? It is in Moscow?
Yes, but it's the University of Idaho.
Weird.
I mean, you put satellite campuses all over the world, I suppose.
Oh, so it's like we need to observe the sky from different points of the Earth.
Exactly. There you go. And basically, they don't know 100% sure that these things exactly exist, but they're looking at gravitational tug from the moon and the rings. And mathematically, these things should be there. So we're going to find out more once we get something out there to actually fly around the big planet, number 7. So
that would be nice.
Quick discussion points here, Dan.
Yeah.
Since we found 2 brand new moons in our solar system of a planet that we thought, hey, we pretty much got this under lock. Turns out we didn't.
Yeah.
Do you believe that there are more moons yet to be discovered on the big gas giants? Probably not the 2 biggest, because we've sent enough crap around that. We pretty much know what's there.
Now, I think the 3 outer planets of the solar system will be ripe with discoveries. Of course, we have to discover Planet 9 100% before we can talk about that. But around Planet 7 and around Neptune, there are still discoveries to be made. We know very little about these 2 ice giants, and we definitely need to orbit them. Send something there right now.
Yeah, it's kind of weird to think of all the stuff. People are looking for planets in different galaxies and around different stars and everything else, and we don't know our backyard yet.
We'll spend a full episode on, at least one episode on each of the planets in our solar system. So we'll talk about them.
We absolutely will. So, Uranus, more stars or not?
Huh?
Uranus. So you said you believe there's more discoveries to be made around Uranus,
yes,
correct?
Yes.
Okay.
Neptune. Yeah, and you said more stars. I think you meant more moons.
Sure.
Yeah, I think there are more moons.
Yeah, they probably don't have more stars.
And I think there are some moons that are pretty hard to detect around the bigger planets. So if you have like a distant moon or a very dark moon, it's easy to miss them. And of course you have these tiny moons hiding in rings. They are easy to miss. Planetary rings are temporary. The Earth has had rings in its past. And if a planetary ring sticks around, there is a reason for it. So there's often a moon involved in making the ring live longer.
You say that they are temporary on a cosmic scale.
Yeah, temporary on the lifespan of the solar system scale. Not temporary on going to Planet 7's scale.
Planet 7.
Yes. You know, that ice giant between Saturn and Neptune.
So if you listen closely there,
yes,
Dan refused to say the name of the planet. Yes. I gave you 5 different pronunciations of the planet, which some people all say are the correct pronunciation of the planet.
It's crazy.
And that's because a lot of the names don't pass the 5-year-old test.
Yes.
Do you know what the 5-year-old test is, Dan?
Yes, it's a very good test that you should do for any new invention, website or project, podcast name. So if you tell the name to a 5-year-old and the 5-year-old giggles and makes a dirty joke about it, then it's a bad name.
And Uranus and your anus do not pass the 5-year-old test.
No, it doesn't. And in Swedish, it's fine. There is no dirty joke involved there.
But in English, oh boy, your anus?
Yeah, it's hard to keep a straight face when you're listening to serious astronomers talk about this planet.
Yeah, and Uranus, even Uranus sounds like somebody's taking a leak.
Yeah.
I like Uranus, but that one is never gonna take.
And it's of course the name of a mythological Greek being, as all of the planets are often Latinized. Always Latinized.
All of our planets.
Yes.
Not all planets.
The old style of naming planets. All of the planets in the solar system.
Correct.
And not even the dwarf planets, but all the main planets.
Yeah. Okay, so, like we said earlier in the show, we got it up on iTunes.
Yeah, it's on iTunes.
So please.
Give us an iTunes review, please.
Yes, please. Go to iTunes, hit that 5 stars, and then you can say whatever you want after that. Just hit the 5 stars.
Yes, if you leave an iTunes review in another country than the US or Sweden, you have to tell us about it because we'll probably miss it. I did check for Swedish iTunes reviews, and we didn't have any, which is not surprising.
No, not with these.
With one episode.
With one episode and the thing being down for a while.
Oh yeah, that too.
I didn't expect much from this one, but please, if you enjoyed the show, go ahead, go to the iTunes, hit that 5-star, give us a review.
Yeah, and please use that opportunity to give us constructive criticisms. Tell us what you want more of in the podcast and what you want less of. If you're already tired about me saying that is a subject of a future episode, then tell me.
Yeah, if you just want me to shut up, let me know.
If you want Angelo to sing, let him.
Yeah, that ain't happening. You can want it all you want. That ain't happening. Strangely, when I
know about it.
When I did pit imps, I used to get people to ask me to sing. That and show me my nipple, but never mind. When we receive emails.
Nobody ever asked me to show my nipple.
That's probably a good thing, because I was always a little disturbed by it. But I streamed my show live, so that was different.
Oh, that makes sense.
Yes. So, emails, if you send them and you put questions inside of them, we're going to try to answer them. So please, feel free to send us questions about anything. It doesn't have to be about our topics or an upcoming topic. Although if it is about an upcoming topic and it's a good question, we will throw it into the show.
Yeah.
And if it's
What's the email address?
It is aofcast@gmail.com.
Sweet.
Yes. And patrons, remember, we will thank you if you, decide to join the Patreon. And we will thank you right about now in the show. So, other ways, you can get a hold of me at twitter.com/FOA Angelo.
Yeah, that's the official Twitter of this show. You can reach me at Dan Horning, but then you will get a lot of stuff that don't relate to astronomy as well.
You will. But remember to go to Facebook, like our page, facebook.com/fan of astronomy, where pretty much everything I tweet I'm going to put over there, plus Dan puts a lot of stuff up as well. So we're going to try to become more and more active as our community grows. Right now, with a smaller community, I don't see the need to really go overboard with the posting of stuff, but as the community grows, we will meet the demand and get as much science stuff out as we possibly can for you. So please go hit that like button at facebook.com/fan of astronomy. So Dan, decent show.
Yeah, liked it.
Got to talk about the sun. Got to talk about how it died.
And next time we'll talk about something that the sun has already killed pretty much.
Ooh, what is our next episode?
Mercury.
We're going to talk about a liquid metal.
We're going to talk about the small pore rock.
Oh, that one.
To the sun.
Okay, that one. Sorry.
And the ice on Mercury.
Ice?
Yeah, ice.
Oh,
some water on Mercury.
That sounds so odd. Anyway, folks, for Dan and myself, I bid you all adieu, and remember that space is very, very interesting, and it always surprises us, like ice on the planet right next to the sun. So please, keep looking out there and be excited about space.
What'd you think? Did you enjoy it? Well, if you did, head on over to patreon.com/astronomy and pledge to these guys. For each patron they receive, the more they will be incentivized to improve the show. So help them out so they can help you out and throw them a couple bucks an episode. They will really appreciate it. Thanks.